video, we're going to talk about equilibrium expressions as well as the Henderson Hasselbeck equation that we're going to use during this titration lab. An equilibrium expression basically tells you the ratio of the product concentrations relative to the reactant concentrations, or products over reactants. These brackets represent concentration or molarities. Now there's two things we're going to exclude from these expressions. One we're going to see when we talk about the equilibrium dissociation constant of water, and the other we'll see when we do the demo Mom to the Rescue tomorrow. So we exclude pure solids and pure liquids from these expressions. So if we were to do the K for water, it's the hydrogen ion concentration and the hydroxide ion concentration over the concentration of pure water. However, since water is a pure liquid, while both of these are considered to be aqueous ions, we can eliminate the pure water concentration from it. So basically, the hydrogen ion concentration times the hydroxide ion concentration is always going to equal 10 to the negative 14th in an aqueous solution. Again, water, pure liquid, can be removed from the expression. When we're looking at acids, we use Ka to represent the strength of an acid. The smaller the Ka, the weaker the acid, because acids, by definition, donate a proton, so the more likely it is to do that, or the higher concentration of protons as a result, means the acid is stronger. So hydrogen ion concentration and the conjugate base over the undissociated acid. If we were looking at bases, since bases are defined as a hydrogen ion acceptor, the products, when you put a base in water, would be the base with the hydrogen ion and the resulting hydroxide ion from water splitting up over the initial base concentration. For the lab that we're going to do, we're going to titrate acetic acid and vinegar. We're going to determine the concentration of the acetic acid and vinegar, and that's in the previous titration video that we did. In addition, the other set of partners within the group is going to determine the Ka of the acetic acid experimentally. And how we can do that is using the Henderson Hasselbeck equation, which I'm going to go over right now. If we rearrange the acid dissociation equilibrium constant expression and isolate H plus ions, we see that this is what we would get. If we were to take the negative log of this, of both sides, we would end up with the negative log of the hydrogen ion concentration is going to be equal to the negative log of the Ka minus the log of the undissociated acid concentration over the conjugate base concentration. Little manipulation of that, we end up with pH is going to be equal to the pKa plus the log of the conjugate base concentration over the undissociated acid. This is going to be useful for us in this lab because what we're going to do is one of the group partnerships within the group is going to determine the equivalence point, or the amount of base required to neutralize the acid. When we get halfway through, that means we're going to have the same amount of undissociated acid and conjugate base. So what that's going to do is make this value 1. And if you take the log of 1, that means 10 to the what power? That would be 10 to the 0 power. So this term essentially disappears, and then we end up with the pH being equal to the pKa. So we're going to record the pH once we get to halfway to the equivalence point, and then the pH at that point will equal the pKa, and then in order to determine the Ka, or the strength of the acid, we just take 10 to the negative pKa. This is also, you hit the button. This is also useful for buffer systems, because you can see that since this is a logarithmic function, a small change in it takes a really large change in the concentration of either of these in order for the pH to really be affected. So some of this could be protonated, and this ratio will change a little bit, but won't really have an effect on the pH. Or some acid could be neutralized, and you could end up with more conjugate base. So that ratio will change, but not that much, and since it's a logarithmic function, it's not really going to have a huge effect on the pH, which is why buffer systems work in maintaining a stable pH set of pH conditions, which is really useful in biological systems.